Okay, here is a lesson on momentum again, but this is the extension material for A-level. So remember, there's a lot of crossover between the IGCSE and the A-level topic. So much of that which we've done before is all relevant. But these are little extension ideas. They're going to try and want to deal with, rather than just the ideas of a diagram and numbers being given to these collisions that take place, they're probably going to want to, so this is before and after, they're probably going to want to graphically try and represent this collision. So there's two types of graphs they're going to use. So imagine this is A, B, A afterwards and B afterwards. And one of them might be looking at the momentum over a given time period. And as this momentum takes, this object A is going to come in with a known momentum because it has a certain velocity of A, and B will have a certain velocity as well. And then it's going to go after the collision takes place between these and have another velocity when it comes out. And we're going to put some numbers to this as well, but first of all I'm going to give you a sense of what the graph will look like. So particle A will have a certain momentum that's that's been given, and then it's going to collide with B, and B will have a certain momentum too, and that stays constant until the point of collision, in which case a collision takes place. And this type of graph should start to become familiar to you. A collision has taken place and there has been a change in momentum. Here is A and here is B. What suggests is, as well, because the masses are constant, what's taking place is that object A has lots of momentum, implying a high velocity, then suddenly a collision takes place and it has less velocity on the way out, hence less momentum. B has a smaller velocity in the same positive direction, because it's all above the graph, remember they're vectors. A collision takes place and it gains velocity, hence gains momentum on the way out. So therefore we need to put some values to this to work out what the change in momentum is likely to be and work out what the subsequent velocities are before and after. So let me put some values to the masses. We have 2 times 10 to the 4 kilograms and 3 times 10 to the 4 kilograms. Okay, so the masses of A and B. Also, the graph is likely to give you some values as well. Here we have the momentum in kilogram meters per second, and on this graph we have 50, this is 20, and then, just to make life easy, though you will probably have to read it off, we have these are at 25 and 45. Okay, so some questions would be similar to, would ask something like, what is the initial velocity of A? What is the initial velocity of B? Let's start with those two. If you think you know what the answers are, hit pause, otherwise here comes the answers. Well, the initial velocity of A is just simply the momentum of A divided by the mass of A, which gives us momentum of A is 50, and being careful here, times 10 to the 3 kilogram meters per second squared, divided by 2 times 10 to the 4 kilograms, giving us 2.5 meters per second. What about B? This is done in a very similar way, just the momentum of B divided by the mass of B. Be careful here, we're looking at this part of the line. 20 times 10 to the 3 kilogram meters per second, divided by 3 times 10 to the 4 kilograms, gives us 0.76 meters per second. Good, it's slightly different the way that we're dealing with this. Usually we'd work out the momentum by giving a velocity, but we can work in reverse. We can work the velocity having known the momentum of these two particles. Okay, what comes next? Well, what about the final velocities, or v dashes? What's the momentum, what's the velocity after the collision for both of them? If you think you know the answer, hit pause, Otherwise, here comes the solutions. Well, all we do here is we read off the values for what A will be subsequently. So we have the momentum of A afterwards divided by the mass of A. 25 times 10 to the 3 divided by the same mass again, 2 times 10 to the 4, giving us 1.25 meters per second. Let me just make sure that sum's right. Hold on, no, it might not be. 25 divided by 20. Yeah, 1.25. Okay, what about B? Well, momentum of B afterwards divided by the mass of B gives us, afterwards is at 45 times 10 to the 3 divided by 3 times 10 to the 4, giving us, just double checking there, 1.5 meters per second. Okay, excellent. So what's really happened here is this, which is moving very fast at 2.5, strikes this one that's only moving at 0.67. And then afterwards, this has been given a shunt to go at 1.5. Let me add the values in there. 1.5. And this has lost some of its velocity, 1.25. It was going very fast. Good, so we've got a complete picture of what's going on here now. Okay, what about the whether it is elastic or not? Now, with an elastic collision, if it is elastic, which is very rare, the kinetic energy is conserved. Okay, now, what I would like you to work out is whether this is an elastic collision. Does the kinetic energy of all of this system before equal the kinetic energy of the system afterwards? So if you think you know whether you can confirm that or not, hit pause. Otherwise, here comes the solutions. Okay, kinetic energy before, or right before, because we don't want to confuse it with B, is going to be a half times the mass of A, the velocity of A beforehand squared, plus a half times the mass of B times the velocity of B beforehand squared. Let's work out what that is. A half by 2 times 10 to the 4 by 2.5 squared, plus a half times 3 times 10 to the 4 times 0.67 squared. And that brings us to a grand total of 69250 joules. Okay, what about afterwards? We do exactly the same. We want a half times the mass of A times the velocity afterwards of A squared, plus a half times the mass of B by velocity of B afterwards squared. So half times all of this is very much the same. We're just substituting in answers. It looks quite complicated, but it's just following through a rather long equation. And that gives us something in the order of 49350 joules. Now these are clearly not the same. There's a difference. Hence it is not conserved. Good, okay, let's move on then. Let's look at a different type of graph. Change of momentum and, of course, impulse. Change of momentum, let's remind ourselves again, is equal to the impulse. Or force times time is change in momentum, which is mass times change in velocity. They might give you an example whereby they give you a force time graph. Force in newtons, time in seconds. And it might look something like this. You'll have to do some sort of interpretation as to what's going on with this particle or object. I mean, here, of course, there is a strong force that's being exerted that peaks at 0.5 and then decreases again, gets to 1. But there is a force exerted throughout the entirety of 0 to 1 second. And they might ask you, what is the change of momentum? Now, there's two ways to learn this. One is to appreciate that the area is the change in momentum. Or you can say to yourself, the area is the same as the y-axis multiplied by the x-axis, which is force times time, which is the same as impulse, which is the same as the change in the momentum, if you prefer. So in this instance, the change in momentum will be, and bearing in mind we have two triangles, we can either assume this rotated over there to make a nice rectangle, or we can do this triangle, half times base times height, times by 2. So the change in momentum will be half times base times height times 2, 25 kilogram meters per second. If they're asking for change in momentum, then your answer should be in kilogram meters per second. If they're asking for impulse, your answer would be in Newton seconds. So keep it consistent. Okay, here's another example. If we have force in newtons with time in seconds, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let's say we have 2, it goes to 4 steadily. And then it continues until it gets to 4 and falls off abruptly. Okay, what is the change in momentum exerted on the object that undergoes this force over that time period? Think you know the answer, hit pause. Otherwise, here comes the solution. Okay, so let's find out the area of the triangle first. This bit here. A half times the base times the height, and then add to that the rectangle, which is merely the height times the base, from the difference between them. That gives us 4 plus 8 gives us 12. Newton seconds. Sorry, kilogram meters per second. Okay, so the two graphical representations of momentum or impulse. Now, what comes next? Well, another leap you need to make to understand for A-level is this idea of Newton's laws actually came about from an understanding of momentum and not force. So whereas you might think of Newton's second law as being F equals ma, really where this came from is force is the rate of change of momentum with time. And I'll quickly describe to you how that goes about. If we take this equation, look at mass times v minus u divided by t, that can be arranged as mv minus mu divided by t, which is actually the change in momentum over change in time. So you might be asked a question whereby you're asked to work out the force exerted if you only have a given momentum, and therefore you must bring this idea to mind. For instance, having said that, if that is the case, then you need to make sure you find this time reference. How much momentum is being changed per time? Or indeed, to make life easier if you want, force is the change in momentum per second. If you don't like differentials, change in momentum per second. Let's give you an example. Let's imagine you've got a jet, a terribly drawn jet, that's firing bullets, and this jet, which weighs 3,000 kilograms, is moving at 300 meters per second, just under Mach 1. Sorry, 350, so just at the speed of sound, 350 meters per second. It's terrible, let me try that again. 350 meters per second, and it fires a bullet of 50 grams going at 1,000 meters per second. And it's firing at 7,200 rounds per minute. Okay, now I want to know what force is being exerted on the plane, obviously backwards, whilst it's firing these for 10 seconds. So the force and then the acceleration for a 10-second burst, and subsequently the change in speed that's experienced. So for a 10-second burst, what's the acceleration and then what's the change in speed? Let's describe what's happening. Okay, so we have the change in momentum is going to be, we have a 50 gram, which turns into a 50 kilogram, 1,000 meters per second, giving us 50 kilogram meters per second. So every time it fires, the change in momentum is 50 kilogram meters per second. How much momentum is there per second? And what we say is now, so the force is the change in momentum, change in time, or the change in momentum per second, which says I've got 50 per shot, and I've got 7,200 going in a minute, so I've got that many going per second. Let me just plug that in. So I've got 6,000 newtons. Okay, so I've got my force. What about my acceleration? Acceleration is force divided by mass. 6,000 divided by 3,000 kilograms, giving me 2 meters per second squared. And for a 10-second burst, the change in velocity is acceleration times time, 2 times 10, giving me 20 meters per second backwards. 350 meters per second minus the 20 gives me 330 meters per second left after the burst. Okay, so it's really important to get to grips with the force is the momentum change per second. Let me show you another example of how that might work. A little bit more advanced, this one, and you might have seen it in class. It's with a helicopter, and you sort of measure that. That's a terrible helicopter. That's my worst diagram so far, but nonetheless. Now, the reason why the helicopter stays upright is because the weight and the thrust, let's call it, of course, are balanced when it's hovering. How is this thrust achieved? Well, it throws air down. This column of air is being forced down with velocity v, and that creates the equal and opposite force, which is thrust on the way up. The change of momentum down creates a change of momentum up on the helicopter. What do we know about it? Well, it has a certain radius. This column of air will have a certain length, and we need to know the density of air. Okay, so what do we do? Well, we know. The change in momentum is going to be the mass of air multiplied by the change in velocity. The mass of air is rho v, the density times the volume of air, times the change in velocity. And we know that the volume is going to be the area multiplied by the length times the change in velocity. The force, in turn, is the rate of change of momentum with the given time, or per second. So if I have rho a L delta v over delta t, which gives me rho a, now look, the length divided by the time cancels to give me another velocity. There I have velocity squared. And finally, pi r squared velocity squared gives me the force, which equals the weight in order to hold it upright. So therefore, and in class we've manipulated that equation, used it to work out the density of air. But the point being is this, that the length of this is being exerted is the same as the velocity. So the length per second of this cylinder is the velocity, the length per second. So all of these problems are referencing that per second nature in order to yield the force. You can do the same if you want with working out for a wind turbine. The air flowing through, and you can work out the kinetic energy per second, half mv squared per second, and work out the power. And there's many examples you can use. But bearing in mind, force is change in momentum per second, and all problems will seem easy. Okay.